What's up everyone, welcome to the Combat Athlete Physio YouTube channel where we take human movement science and we bring it to the combat sports. Today we're doing something a little bit different. We're going to take a little bit of a deeper dive into the science of knockouts. More specifically, why a fighter actually loses consciousness after a strike. Now if you've been watching me for a while, you know that I've covered this topic before, but this one is designed to be a lot more detailed. This will be my best interpretation of what the current research actually says. And while we go through this, understand that there's not really just one singular explanation. The science points to more of a spectrum of mechanisms, some with much stronger evidence than others. So what we'll do is start with more of the weaker, more outdated ideas and build up all the way to the leading explanation of what researchers think best fits what's happening scientifically when someone gets knocked out. We're going to start with a visual so you can better understand kind of how the mechanism works. So really the main story that I want you to visualize here is twofold. Okay, so we've got a fighter like Takeru who's getting hit with a left hook by Rodtang. Okay, and it starts here just before contact is made. So whenever contact is made, it is an acceleration into rotation. So I'm going to go as slow as I possibly can here, frame by frame. And when he gets hit, he accelerates into left cervical rotation. Okay, so that is just rotation of the cervical spine to the left. This acceleration and then subsequent deceleration. So whenever he gets hit, these muscles and the ligaments and tendons and joint structures go into their end physiological range. It decelerates and then comes out of that position. What that does is, remember, we've got our brain being housed up here in the cranium, sitting in something called cerebrospinal fluid. And so whenever we get hit and it accelerates and decelerates, it doesn't have to be rotational, but some of the research would suggest, actually a lot of the research would suggest that these mechanical forces that we're going to talk about here soon are highest in the rotational planes, okay? And if you don't understand what rotational planes are, or you want to understand better movement, I have a free biomechanics course that's going to be linked in the description if you want to learn a little bit more about that. So this acceleration into rotation and deceleration out of rotation puts a lot of traction or shearing or tension on the nerve tissue of the brain. And that's kind of the picture that I want you to have whenever we're talking about a lot of these terms that we're going to use. It's all related to this mechanism that's happening here. So one more time, acceleration into an end physiological range. It whiplashes out of that range, and then it puts a lot of tension on the nervous tissue within the skull. Okay, so now that you have a little bit better of an understanding of that rapid acceleration and deceleration mechanism, let's zoom in even more onto the nerve, or something called a neuron. Every neuron has a cell body, dendrites that receive input, and a long axon that sends signals. And wrapped around this axon is the axonal membrane. These neurons are constantly firing through rapid ionic exchanges. And ions, for those of you who don't know, are just tiny molecules with an electrical charge. So consciousness itself, or alertness, if you will, is basically billions of these neurons acting in rhythm. So when a strike disrupts that system, or enough of that system, even if it's for just a few seconds, the whole network can just go offline. So we've got a good visual of the mechanism, and we've got a decent understanding of the basics of the neuron. Let's use that understanding to walk through these different theories that researchers have put forth to explain this acute loss of consciousness. The first mechanism we're going to talk about is referred to as brainstem network disruption. This one has the weakest amount of support. This one says that a knockout occurs because of a disruption in the reticular activating system, which is located in the brainstem and is basically the on-off switch for consciousness. This was known as the reticular hypothesis for a long time, and it kind of made sense. The brainstem is a part of the brain that's central to arousal. So if you disturb it, it would make sense that you just go lights out. And while modern imaging does show that damages to these networks can contribute to longer-term disorders of consciousness, it doesn't explain the immediacy of a knockout, because a punch can drop somebody in a split second, as we've seen. And the reticular theory really doesn't line up with how fast this happens. So today, this is seen as more of a part of the picture, potentially, particularly in long-term issues, but probably not a primary cause for the acute loss of consciousness. I'm going to refer to mechanism 2 as vascular factors. These have a moderate amount of support, and exactly as the name suggests, it points to blood flow. Here, the idea is that the strike causes a sudden drop in cerebral perfusion. Studies using MRI and other different ways to measure blood flow have shown that head impacts of a certain degree can cause something called hypoperfusion. And this just means reduced blood flow to certain regions of the brain. And we know that if the brain doesn't get enough blood, alertness or consciousness fades pretty quickly. But really the problem with this theory is that this happens over minutes to hours, not typically instantaneous. So these vascular symptoms, again, may contribute to symptoms after something like a TBI or concussion, but it really wouldn't explain the reason that a fighter collapses as soon as their chin gets touched. So again, it's probably part of this spectrum of mechanism, but probably explains less of that knockout button itself. Mechanism 3 is diffuse axonal dysfunction. This has some pretty strong support, and it certainly brings us closer. Remember when we went over how the head spins and then violently stops? Well, when that happens, those axons that we also talked about, the ones that carry the signals, those structures get stretched and sheared. Now, we're not talking about them just snapping completely. That's a whole different issue. We're talking about really subtle damage that happens to the structure of that axon and can impede how signals are being transmitted. And like I said before, this really has a lot of support in the concussion literature. Imaging studies and animal models show that rotational acceleration causes axonal dysfunction throughout the brain. And this could explain why our consciousness gets scrambled so quickly. But here's the catch. Those structural changes that we see don't really happen on a millisecond timescale. So while it is documented that diffuse axonal disruption is a very real phenomenon, it's still not quite fast enough to explain that immediate lights out that we see in combat sports. But like we've been talking about, it's a spectrum, and it's definitely a part of the picture, a much bigger part of the picture than the other two. And much like the other two, it offers another explanation for why concussions offer longer recovery sometimes. And mechanism 4, with the strongest support, you've heard me say this before, mechanoporation. Mechanoporation is the mechanism with the strongest current evidence. So picture the head rapidly accelerating again. When that happens, those membranes of the neurons that we talked about before stretch and they form tiny, reversible pores. These pores allow those ions that we talked about before in an uncontrolled way to flood across the membrane. Think of it sort of like poking a hole in a water balloon. Suddenly, the very thin layered system that kind of holds everything at equilibrium is disrupted. And because neurons rely on that membrane equilibrium to fire in rhythm, it can disrupt large neural networks pretty much instantly. And under this theory, that's why a fighter would go from fully conscious to lights out before even hitting the canvas. But the beautiful thing that really sets this theory apart is that it matches recovery time. There's evidence that these pores can reseal seconds to minutes after the injury, so that balance of ions of the membrane can be restored. And then the fighter might regain consciousness within that seconds to minutes time frame, which is what we often see in fighting. Now, this is certainly not perfect. There's still a lot of ongoing research. But as of right now, mechanoporation explains both the speed and recoverability of knockouts, really better than any other model that I can find. So just to recap, we've got brainstem network disruption, which is a possible contributor, but probably too slow and indirect. Vascular factors was mechanism number 2, and it's definitely involved in concussion physiology, but probably not the knockout switch. Next, we have the diffuse axonal dysfunction, which has really strong evidence in concussion and can help us explain lingering symptoms, but not quite fast enough to account for that split-second loss of consciousness. And then we have mechanism 4, mechanoporation, which is the model that best explains both the immediacy and the temporary nature of knockouts. And again, I cannot stress this enough. It's not about picking just one. These mechanisms exist on a spectrum, and in reality, it's probably multiple processes happening at once. And the point of this video is just trying to single out what we thought the primary driver of a loss of consciousness is. So the next time you see somebody get knocked out, you can appreciate the amount of science that exists behind that one single moment. It really is a complex cascade of mechanical forces and neural disruptions happening in milliseconds. If you found this breakdown useful, make sure you hit that like button. It really helps the channel out. You can also drop a comment below. Let me know what you thought about the video, or tell me what you want to see next. Thank you guys for watching, and I'll see you next time.